Okay, so polynomial function, very simple. It's just going to be, I think I already defined it in the last class. I don't remember. But it's just a function with more than one term, and each term is in the form of a times b, sorry, a times x raised to the n power. There we go. Yeah, can I do mine? I'm just kidding. Right. Just being sassy. Yes, of course. Let's realize it. Okay, so yeah, that's all it is, and we know what a to the xn is. That just means why did I do that? Oh, whatever. Red. There we go. Yeah, it's the same thing as saying a times x raised to the n power, right? So every term is like that. So a good example would be like this. What if you have like y equals, I don't know, x cubed minus 2x plus 1? Do I have more than one term? Yes. Is every term in the form of something times x raised to the n power? Yes. Right. So yeah, so this is okay. Now let's talk about the first example. This should be pretty easy. To be a function, you guys should know this already. So again, all this is review from Algebra 1. Excuse me. Let's see here. To be a function, must pass vertical line test. You guys know this, right? Vertical line test. And what does vertical line test exactly entail? If you draw vertical lines, it should only touch once. It can never touch more than once. So I think all these would be. Definitely this one is. If I drew a vertical line, that passes. That passes. Okay, not exactly vertical, but that passes, right? I think this one does too, and I think this is just a typo because that's supposed to be a hole right there. So that hole is just a little off-centered. This would pass also. So all of them are.
Are all polynomial functions?
They are, yeah, actually, and that's good. That's the whole point we're trying to get here. All four graphs are functions. So the key takeaway, all polynomial functions, sorry, all polynomial equations are functions. That's key takeaway. So yeah, we're good. It all makes sense. Okay, let's keep moving. And behavior notation. You guys prize this in algebra 2, I think. So M behavior, you have there's 4 cases. Here are your 4 cases. So the arrows could both point up, both point down, or left is down, rise up, rise down, left is up. So those are the 4 cases. M behavior notation, you write like this.
When?
Yeah, I'll explain what that means in a sec. So this is why did I choose purple as a dumb color? This is abbreviated for the word limit. So the way this is interpreted, here's how you interpret it. And this is definitely something that you're going to see often in calculus next year, like probably first week, if you're in college or first week of college, you'll see this stuff. Next year, if you take calculus here, you'll see this first week. The way it's interpreted is that the limit of y as x approaches negative infinity. That's what this means right here. And then the other one, I don't know if I can copy and paste. Nope, that's something else. Gosh darn it, what did I do? Hold on. That was dumb. Good thing it wasn't a super sensitive text. I could copy and paste it there. That's embarrassing. All right. Okay. And then let me write for the next one. Next one is this: the limit of y as x approaches positive infinity. Now, let's take a look at this scenario here. I'm going to highlight it right now. Let's look at that scenario. That's a graph that would look like this. I'm going to do it off to the side here. What equation do you think I just drew? So if you're given an equation, y equals x squared, sure, right. Okay, what happens to both arrows here? Are they both pointing up, both pointing down, or opposite? They're both pointing up, right? So here's what you have to figure out. What is y doing as x goes forever to the left? When x goes forever to the left, y is increasing, yes. What happens when x goes forever to the right? What's y doing? So what you're going to do is you're going to write this: positive infinity and positive infinity. I'll summarize this on the next page, don't worry. But that's what you would say. Like, they're both pointing up, you say the limit's positive infinity because y is going up forever. Very good. So what limit does y have? Is there a limit at y? No, there's no limit, right? It just goes up forever. So that's what when you write end behavior notation, what you're telling me is that what does the end of the graph do? That's what we're trying to figure out. What is the end of the graph doing? So let me let's see if there's a table. Let me do this. Let me back up a little bit. Let me clear this. Let me do a whiteboard. Here we go. Okay, let's do this here. This will be a little easier, I think, for you guys to understand what's happening. Let's say you have y equals x squared. Y equals, I'm going to create a quadrant here. Y equals x cubed. Y equals negative x cubed. I'm going to do quick sketches. And you guys don't have to write this down. You can just sort of just watch first. Okay, so let's look at y equals x squared first. Let's focus our attention here right now. What happens to both arrows both pointing up, right? So here's how you would write it. You write as the limit. No, it does exist. I think you're quoting a movie. It's Mean Girls.
Yeah.
Yeah, I've never seen it actually.
Is that a TV show?
Is it?
Gossip Girl.
One would be the limit not exact.
That's if you're going towards, well, I don't want to get into that just yet because that's just a longer discussion. We will get there. Okay, so now let me explain what's happening here. So both arrows are pointing up, right? So when you're going forever to the left, what does y do? It's pointing up. That's what you put positive. When you're going forever to the right, what is y doing? It's pointing up. That's what you put positive in as well.
Okay.
So now,
Wait.
let me copy and paste this Can't copy and paste, crap. So let's look at this one now. The limit as x approaches positive infinity of f of x equals, and the limit as x approaches negative infinity of f of x equals. So now look at y equals x cubed. Look at the right arrow. Is the right arrow pointing up or down? Is the left arrow pointing up or down?
Down.
So you're gonna write negative infinity for the left arrow and positive infinity for the up arrow. That's all you did. So that's
And you'll
exactly, yes.
give us the graph, right?
Yeah, I mean, I'll make you graph something and then state the end behavior. And then these would be the opposite of the first one. And notice I'm writing the limit next to each arrow just so it's clear what I'm doing. Sorry, I'm kind of
Y equals x to the negative.
okay. That's rational functions. We're doing that later in this unit. Yes, we're doing that. So yeah. So the other thing too, I forgot to mention, the exponent has to be a whole number. Yeah, I did mention in the last class, but the exponent does have to be a whole number. So write a times x to the n. N is a whole number. I forgot to mention that. Yeah. Lastly, here the limit as x approaches positive infinity of f(x) will be negative infinity in this case. And over here, equals positive infinity. So yeah, that's all. Okay. So hopefully that kind of makes sense. And I should actually give you guys a table that shows all that, so you guys have like some reference. So I'm gonna clear this for now. I did record this, just so you know. So now let me stop sharing the whiteboard, share the full screen. Okay, let's move on to this here. So you're asked to describe the end behavior by filling the blanks. So we could go to Desmos, or I could do this in my graphing calculator. I'll do my graph calculator so I don't have to go, so I don't have to toggle screens. So what if I graph 2x cubed? There you go. That's 2x cubed, right? The arrows look like this. Left arrow, right arrow. So in this case, describe the end behavior. You see the limit as x approaches negative infinity. The limit as x approaches positive infinity. And just to make our lives a little easier, I'm not going to write this over and over again because it's going to take too long. I think you guys are going to revolt if I make you guys keep writing this. So I'm going to make like a little table here. Okay, I'm going to make like a little table here. I'm going to do likewise down below as well. So limit just means, if there's a limit for y, or what's y approaching. Okay, now just do green here for all the answers. So y equals 2x cubed. What happens to the right curve? Sorry, the right arrow. It's pointing up, right? What about the left arrow? Down. So you're going to say positive infinity here, negative infinity here. Now, what if I replace this 2 with a negative? What materials now? They reverse, right? I need to plug my laptop. Cool. So in this case, they're reversed. That's positive infinity, and that's negative infinity. What if I replace this negative back with a 3 and do x to the 5th power? It's just like part A, right? Just like part A. Two x squared, negative 2x squared. So negative 2x squared. You guys should know what's happening here. Both point down. Negative infinity, negative infinity. If I do 0.6 x to 6 power, 0.6 x to 6 power, they're both going to point up, I believe. Yep. Good. You're getting it now. Good. So there's a pattern here, guys.
Oh, now, while that's about patterns, right? You gotta look at two things, the exponent and the leading coefficient, that's it. The exponent and the leading coefficient, all you have to look at.
If the exponent is even, the arrow's going to go in the same direction. If it's odd, they'll go opposite direction. If the leading term is positive, then you can expect both arrows to point up, assuming that you have an even exponent, or both arrows point down if you have an even exponent with a negative. But then when it's odd exponent, they just switch. So
And where it's an odd, trying power,
Mhm.
and it's like,
right, so if it's positive and odd, then it goes left down, right up, and then reverse the other way. So let's write this out over here. So what you want to do is focus. So the key takeaway here. Yellow is no good. Let's do green. I'll do purple. Key takeaway. Focus on the leading term. For determining, bless you, and behavior. Okay, that's a key idea. So totally, 100% you can. Yep. So given a polynomial, I don't know what's meant by this. Oh, a sub n's the leading. Okay. This is weird. Let me just cross this off here, guys. That's just weird. So say, for example, f of x equals a times x to the power plus dot, dot, dot. Where n is the highest. Oh, bless you. Allergies, right? Highest exponent. Where n's the highest exponent. So if n is even, you can have this, or you can have this. If n is odd, you can have this, or you can have this. The first one's true if a is positive. This one's true if a is negative. This one's true if a is positive. This one's true if a is negative. That's it.
That's how you generalize the NBA. If your leading term has an even exponent, both of those go in the same direction. That kind of makes sense. Even, they go in the same direction, right? Positive, you're on the up and up. Down, minus, go down. Makes sense, right? Odd, the arrows are odds with each other, right? They're going opposite directions. That makes sense, right? Arrows go in opposite directions. No standpoint. But positive, that means it ultimately ends up being up as it goes to the right. At the end, you're just going to be positive. But here, a is negative. That means ultimately you're going to be going down as it goes to the right. Ultimately, it just shoots down forever. Off to the right. So that's it. That's end behavior.
arrows are, it really is negative and positive.
Well, combined. Even and positive, they both point up. Even and negative, they both point down. Odd and positive, it's down up. Odd and negative is up down. Yeah. So without graphing, you could totally do this without graphing. Now I'm gonna write the end behavior for each of these right now. I'm gonna do the limits as f of x, sorry, as x approaches negative infinity. And I'll do a little table here. Kind of frustrating to write this over and over again. By the way, when we do get to calculus, you will have to write these limit notations a lot. Just saying. It does. But trust me, when you get to later stuff, it gets cool. You have to take it at the Navy, right?
100%. It's a huge amount.
Yeah, right. Yeah.
Yeah, that's why I'm in pre-calc, because you have to take out
You
this
have to
no matter
take
what.
it. Even if you already.
Yeah, so, and I heard.
The first 2 to 3 weeks is what you just said. Not great. It does get better. So it does get better.
But it's mandatory, it doesn't matter. Take it, like, pre-calc, like this.
Oh, even if you have AP and got good AP scores, really? Okay.
Can do a higher one, but generally. majority of the-
It's good to do it again anyway. It just reinforces these skills. So here's the deal. We're odd exponent, positive coefficient. Positive leading let me write that again. Let me make it more clear. Sorry guys. Here we go. So part A, I'll do the text box. Odd exponent and positive leading coefficient. And then this other one over here. Even exponent and negative leading coefficient. And what you're doing is you're focusing on the term with the highest exponent. So you're focusing on here or here. Use the curveball because the highest exponent was actually the last term listed. Doesn't matter what order it's listed in. You gotta go with the highest exponent when you're doing the end behavior. So now, as I go further to the left,
Odd exponent. I'm going further to the left with a positive leading coefficient. I know my arrows
have to look like this. I know my arrows have to look like this. Down, then up. Whereas for B, they're both down. Because it's even with a negative coefficient. But A was odd, but positive coefficient, so it finishes up at the end. What am I going to write for in terms of infinity for each one? So as x is approaching negative infinity, we're going to say for part A. Yeah, because the arrow is pointing down. How about for the other part? Oh, sorry, for x approaching positive infinity for part A. Yep. And then what about for part B? Both negative. That's it. Okay, I think I beat this to death. So I got to do this again. B period. No joy. All right, so that's all there is to it. Can I move on?
Yeah.
Yep. Okay. All right. Now we're going to talk about finding x-intercepts. This is a little more interesting. I like this stuff better. So again, you do need to know what these terms are. Like a zero is just an x-intercept.
You guys want x-intercepts are just one touch y-axis. That's when y is 0. It's also called a zero the function or a root or solution. But also say exponential factor because if you factor it, 6 factors equals 0, and x would equal a.
Right. So upon the function degree n has at most local extrema are mins and maxes. And zeros are x-intercepts. So for example, like what if I have a curve that like that does this? This is a cubic polynomial, by the way. What does cubic mean? 3. Cubic 3. So if your polynomial has a degree n, degree is the highest exponent. Degree is
What does that say next to the zero?
x-intercepts. So highest exponent. So you have at most n minus 1 local extrema, at most n zeros. Extremas are the high and low points.
So this, for example, is a cubic function. How many high points or low points do I have combined? 2. And how many times do I touch the x-axis? 3 times.
So whatever n is, the most x-intercepts you could have is n itself, and the most highs or lows combined will be n minus 1. Let me actually graph part A for you guys. Here we go. Let me graph part A for you guys. So what if I had clear 3x, gosh darn it, 3x raised to the third minus 5x squared minus 2x. Okay, so if I were to zoom in just a tad, so how many times does touching the x-axis, guys? 3 times. And how many highs and lows does it have combined? 2. There you go. So if I did like a degree 4, they could have 4 x-intercepts and at most 3 highs and lows. There is a possibility that it may not touch the x-axis 3 times. You know, it could touch just once. That could happen. We'll talk about that. But in this case here, find number of extrema and zeros, 3 and 2, and that's because n equals 3. And actually, this question should be rephrased. Find the highest possible. That should have been snuck in before the word number. Highest possible number of extrema and zeros. So let's look at another one here. Or 2 more here.
Wait, can we graph over and
Oh, sure. Yeah, it's right here. There it is.
oh.
Yep. Yeah, the graph looks like this. Yep, just looks like that. Okay. Let's look at part B. Same thing. Extrema 2, zeros 3. Right?
If it's negative, like, would it still be the same? For the extrema and zero?
Totally. The end behavior would be different, of course. And the end behavior would be different. What was that? Yeah, let me zoom out. There we go. Yeah, so wait. Yeah. So anyway, yeah, you're right, 3 x-intercepts and 2 extrema, right? And the reason why we're doing this, just I know it's not very exciting stuff, but as you move on to calculus, you have to know how these graphs look and behave so that you can actually do calculus principles too. So that's why we're spending this time doing it, because you can't like be in calculus and all of a sudden like, wait, what kind of graph is? How does this graph look? You want to make sure you've got a clear picture of these graphs act. And that's why we're dissecting it as much as we are now. Let's look at part C. Part C, let me graph in the calculator. That would be a good idea. Let me go and clear this. Well, I'll give you something that you can ease. We are going to do some graphing without a calculator, but I'll give you something that you can factor. Because you can factor, then you can figure out all this stuff pretty easily. I'll give you something that's factorable for sure. Factor pulling out common factors, and then maybe not quad form, but just a quadratic equation that you can like use a diamonds. Yeah. Oh yeah, 100%. Yeah. Okay. Let's graph this one here. Let me zoom in. This is hard to see. Is that JP Hassan Owen making noise in the hallway? Oh, okay, clear sense. Okay, I can make sure that being disruptive to the classes. Okay, so this one's kind of interesting.
What do you notice about this peak here? It's right on the x-axis. Likewise with this one also.
Yeah.
So this one could have 4 x-intercepts, but we see just 2. And there are 3 extrema. Just 3 extrema. You guys need to get caught in the notes, or you guys need to get caught in the notes, or okay, no worries. So let's dissect something with part C just a little bit. Before I move on to the next page, you don't have to write this down, but it's just kind of good to talk about. Can you factor anything out of this? Part C? What can we factor out? Good. I like that. X squared. Actually, I'll do one better. I'll do negative x squared, yes. So what's left inside? X squared minus 4x plus 4, I think. Can you factor even further? Can you factor even further? That's the polynomial that's inside the parentheses. Go ahead. They're both identical, x minus 2.
So you can see that in only x-squared x-intercepts 2, because these are repeated, right? And 0. And so that's why
we're seeing a bounce off the x-axis. You're seeing the graph bounce twice off the x-axis because
even though it's 2 to 4, we don't have 4. When I calculated, these are right there. And then negative x squared, that's just 0. He said he's back. Yeah,
the whole point is, how do we find x-intercepts in the first place? What do you set the equation equal to? Exactly. And once you have it factored, you can solve for x, right? Because then this would have to be 0 to make this equation work. This would have to be 2. This would have to be 2. So we're only seeing crossing it twice, even though the degree is 4. So this next one's kind of a big example, and then we're done. Then you guys can get it. You guys can start the homework. And we'll do the homework quiz right after this too, which is, anyone do ACT tomorrow? Okay, so you'll like, not too bad. It's not too bad. 2 years ago, people had to fly to Arizona or Idaho, just so you know. That was crazy. Actually, the craziest story, let me just pause this for a sec. This is the craziest story.